Hello everyone, welcome to Tactica Imperialis and to today's video. Today marks the start of my science teaching video series. This is going to be a regular fixture on the channel for at least the next few weeks. What with current events being what they are, I want to provide that teaching resource. You may have seen the video I put out recently. If you don't, I'll link in the description to it. And from that video, I got a few suggestions from the comments, so thank you comments, and I'm going to start with one of those today. The topic of today's video is a GCSE triple science physics topic. So if you are doing the UK GCSEs, then triple science demands you know this. If you're on combined sciences, I'm mainly talking about the AQA specification here. If you're on combined science, you don't actually need to know this for your exam, but this is some very useful physics nonetheless. And if you are a triple science student, then at least at the current specification, you do need to know it. So we're going to go over it. Now, even if you're not a triple science student, or this is not on the specification that you know for your test, I still think this is a video worth watching. Not just because I'm making the video and therefore I think it's good, but because lenses come up all the time in everyday life. They're how your eye works, they're how your cameras work, they're how your glasses work. All sorts of things use a lens. You could probably come up with a giant list in the comments if you wanted to. Now, I'm not going to do this in a full me sit, talk, you listen format. I'm going to try and create a little lecture section, and then I'm going to give you some questions as an exercise that you can do to work on it at home. Obviously, I'm not going to ask you to hand them in, that would be ridiculous, but I don't just want to give you the information and then dump it. I do want you to actually do a little bit of work rather than just sitting there passively listening. So, sorry. But what we're going to do for this video, as I said, we're going to do lenses, but before we do that, we're going to do the bit that makes lenses work, and that's going to be refraction. Now, even if you're not a triple science student, I think you do need to know this, so you may want to stick around for the first 5 minutes. But we're going to recap refraction, then we're going to go over the two types of lenses and the terminology about images that you will need to know. Of course, I'm going to get this right in terms of the science, but I might get it wrong in terms of the presentation. This is my first teaching video, so let me know in the comments if you have any thoughts about the format, the presentation, the way I do the lesson. Please do let me know, because that's the only way I'm going to improve. I'm not psychic, I'm not a genius, I'm just a teacher doing their bit. So let me know what you'd like me to do in the comments in terms of improving the format of the video. But with that said, let's get started with refraction, and then we're going to move on to lenses. Okay, so here's the first activity that I'd like you to have a go at as part of today's lesson. Just a bit of revision, hopefully, before we get on to lenses in particular. So on the board, I've written out a couple of sentences. Apologies to those of you who are perhaps a bit more visually struggling, because I don't have a yellow board or something that I can write on. But if I create any supplementary resources, I will try and put the pages in another colour, since I don't have to print them, so that you'll be able to read those. But the sentence reads, for those of you who are struggling to read it because my writing is awful, as follows. When light enters a blank with different density, it changes blank and bends. This is called blank. When the light blank, it bends towards the blank, and when it blank, it bends away. So I would ask you now to pause the video, give yourself as long as you think you need. I would recommend you probably need about 3 minutes at most to work it out, and then have a go at it, see how you do when we come back. So I'm just going to let you pause the video and have a go. All right, so hopefully you've had a chance to have a go at home. So this is all about, in fact, probably the easiest word to start with is this one here. So if you were struggling, I'll give you that one. How's that look on the camera? It looks fine. So this is all about refraction. So this is what this activity was all about. And I'll go through the answers now. Hopefully, if you want to have another go now that you know what refraction is, take a second. Okay, you had a go. So when light enters a medium, A medium is a word you need to be using. It's a very important piece of terminology. With a different density, it changes speed and bends. Now, you might have heard and guessed at changing direction. Now, you'd be right in that the light does change direction. I'll draw a diagram in a moment to show you what I mean. However, that is due to a change in speed. Now, I've written this mainly with higher tier candidates in mind because the lenses lesson is for triple science. But this stuff you should know. Certainly, you should know this bit. This bit here, this top sentence, is probably higher tier. This sentence at the bottom, everyone should be able to do. And this process is called refraction. When the light slows down, it bends towards what we call, and it's another piece of terminology, the normal. Now, the normal, I will show you in a moment, and those of you who are my Warhammer subscribers know don't make the joke. The normal is an invisible axis, if you like, perpendicular to the surface. And when the light speeds up, it bends away. So there's 1, 2, 3, 4, 5, 6 sections, or 8 words if you like. Give yourself a little mark, see how you did, and I'll give you a couple of seconds now to pause the video and make any corrections if you're making any notes. Okay. So let me now put this sentence, which hopefully you'll have written down so that you can rewind the video, so that you can see exactly what I mean by refraction and normals and all of that jazz, because this stuff is really important when it comes to explaining how a lens works. So I'm going to draw here a box, and this box is going to be made of, let's say, glass. We often use glass. Particularly with prism experiments, you'll see things made of glass. Now, the normal is like this. The normal is an axis like that. It's an invisible line, and when a light ray, not a beam, a light ray is incident on that surface, so we're going to make the ray travel in this direction, and we're going to say this is air, and we're also going to say that this is air. So, my light ray is coming in this direction, and when it gets to this boundary, if you like, I'm starting to use some slightly longer words than you might need to know, but I'm going to try and use them for the sake of completeness. When it gets to this boundary, the glass is a lot denser than the air. So density, mass over volume is a formula that you certainly meet in triple science, and possibly you meet in all sciences. In fact, I'm certain you do. So glass is denser than air. Now, what we said in the starter, if you remember the little fill, is that when it enters the glass in the denser medium, it changes speed. Now, when you enter something denser, think about walking through the air and then trying to walk through treacle. It's not particularly pleasant. You slow down, and the light does the same thing, meaning it bends towards the normal. It would travel in a straight line. I'm doing this on a whiteboard, so it's slightly approximate. So this angle, let's say that's 30 degrees, will be greater than this angle. Let's call that 20 degrees. This is the angle of incidence. This is the angle of refraction. This is stuff I'm sort of getting into A-level things with refractive index, and you can actually work these angles out. Don't think you need to, don't worry about it. But when the light gets to the other end of the glass block, I'll draw a second normal, because there's 2 normals. We're now going back into the less dense area. So that's less dense, that's more dense, and this is less dense again. So as we're coming out, the light ray will bend away from the normal. Something like, get my angle right, something like that. And quite cleverly, which again I don't think you need to know, that angle will be the same. The light will travel back on the same path that it was going in with when it comes back out. Obviously, approximate, not drawn with a ruler. If you do a diagram, particularly in an exam, draw it with a damn ruler. So that is refraction summed up. Light enters a medium with a greater density and bends, changes direction towards the normal. And when it leaves again, it bends away from the normal. Now you can do this in terms of waves. So if you think about this as a wave front, then part of the wave slows down first and it sort of turns the light a little bit. Then when it leaves, this part speeds up first, so it turns the light out again. That's something you can look into, but that's what you need to know in terms of refraction for a lens. So that's refraction. Now we're going to move on and talk about one of the two types of lenses. I think we're going to start with convex lens, and then we'll go from there. Okay, so now we're actually on to lenses, and we're going to start with convex lenses. So C-O-N-V-E-X, convex lenses. So a convex lens expands outwards at the center, if you want a way to think about it. So you have an expansion of the lens, meaning it is fatter at the center. If you were to draw this in a ray diagram, you would also see it drawn, and you should probably know this, drawn like this. So line with two arrowheads pointing outwards. Later in the video, we're going to meet concave lenses, and they have the opposite symbol, but we'll get to that when we get to that. So a convex lens is usually made of glass. So we need to think about what we do when we get a lens and we have a change of density. So let's have our light ray, shall we? So light ray comes in. Now I need to draw my normal. There's my normal. So following the principle of refraction that we just discussed in the last couple of minutes, we know that because we're entering the denser lens, so we're going to again assume this is air and this is glass and this is air again, same assumption, the light is going to bend towards the normal. So it's going to bend something like that. However, what's changed from our lens to our glass block? Well, before we had two flat edges for our block. So it's one edge, bish, bash, bosh. Something like that. It was a little bit more accurate than that, but that's what it looked like. Now we need to again draw our normal perpendicular. So I'm just going to that about right? That looks about right. And now we know that the light is going to bend away from the normal because we're going back into the less dense medium, that being the air. So it's going to bend like that. So that is the path that the light will take as it comes through a convex lens. And you'll see this across all ways in, with the one exception of the light ray that is incident at the center. So that one, your normal is like that, and your normal is like that, so your beam just carries on through. All other light rays, aside from the one right through the center, are focused in, and that's the really important thing about a convex lens. So if I was to do this again, come in from the bottom, here's my normal, bend towards it, here's my new normal, bend away from it, bang. And what's really, really clever about a convex lens is that all the light is focused and will pass through one point. Now I've drawn a bit of a hodgepodge diagram, so when you do your lens diagram, make sure you get this bit. So there is a point here at which all rays pass through. It doesn't necessarily have to be there. It could be over there. It could be here. It could be here. But there is a point at which all light rays pass through. And it focuses on that point. Now this point, as the place where the light is focused, has got a name. We call it F. And you won't be surprised to know what I'm going to call this. We call it the focus. In fact, we don't just call it the focus. There's a little bit more to it than that. We actually call it the principal focus. Why? Primarily, I'd guess it's because all of the light rays are focused on it, so it is the most important focusing point. You might be able to focus at a different length, but that is the main one, so it is the principal focus. We also give a name to the path, the axis of the central ray. This here this line is called the principal axis. So the ray through the center travels along the principal axis, and the light rays all pass through a point known as the principal focus, which is F. So let's find a way to get that on into some notes, and then you can pause the video and you'll be able to take it down. I'll leave this up now, so pause the video. If you need to do a drawing, do so, and then I'll make you some notes. Okay, let's clear the board. So, key takeaways for a convex lens, and we will do about ray diagrams in a moment, but here are the key takeaway points. So, the ray through the center. Now, I'm going to write in a bit of shorthand. I suggest you write in longer form than this, but I have only got so much whiteboard to space. Center travels on the principal axis, not refracted. So what we mean by that, it travels in a straight line and its path does not change direction at any point. All rays, and we do mean all of them, pass through the principal focus, which again has a name. It's F. I know we use F a lot. You'll have seen it for forces, but in this case, we're talking about the point that all the rays pass through. So again, I've got the back end of my lens there. There's the principal axis. All the rays are going to pass through one point. Terrible drawing, but that's it. So that is the basic principle of what a convex lens does and what it looks like. But what are the things you'll probably be asked to do? In fact, leave that there. There, you've had a chance to take some notes. So what you now need to do is be able to draw a ray diagram. Now, I'm not going to get into the ins and outs of everything you do with a ray diagram, because hopefully you'll know the basics by now. So first we need to draw our lens, and I'm going to use the symbol that I introduced to you earlier. So there is my convex lens. We'll just make it simpler and get rid of all the double refraction lines by just making it one. We then draw our principal axis, and I'll just draw it as a dotted line because it saves it being confused with an actual ray. What we then need to mark is the position of the principal focus. You'll usually be given this as an actual number in terms of the distance from the center. So there's F, and this distance here, if you care for it, is called the focal length. So you might have heard of focal lengths or something to do with focal anyway, if you do optics and opticians. So you might have heard of that. So focal length determines where the principal focus is. It's at that distance, but that's kind of an aside. So we're going to get rid of that now. Thank you very much. When we're drawing our ray diagram, we have two steps to the process. The first one is to draw our object. And for that, we're going to do an arrow. And we want to position it. It depends really on what your question asks you, but where you place it determines what the image actually looks like compared to before. So let's say that's that far. That's one focal length, and that's two. So there are two steps to your ray diagram once you've drawn your object. First, you need to draw a line from the top of your object straight through the center of the lens. So again, you get a ruler, you go straight through like that. The next line you draw, again, comes from the top of your object, and it goes horizontally to the lens and then through the principal focus. Now, I've drawn a diagram where I'm going to really struggle here, so you will do a better one because you'll have more paper than I will. I'm just sort of ad hocing it. fact, I'm going to do that one again. So that's what you do, but we're going to draw it a little bit smaller to make my life a little bit easier and help you see exactly what's going on. So clear that. There's the lens, there's the axis, there's the focal length, and there's the object. That's a little bit easier, isn't it? There we go. So, same principle. Line through the center, straight line, bang. Second line, straight across to the center of the lens, and then through the principal focus. And then that line carries on, and that line carries on. And what you then do is you see where the two objects meet. So you see those two lines came from the top of the arrow. So these two lines now form the top of the arrow. And you draw your object. That is all you have to do for a ray diagram. It's two lines, 1 and 2. And where they get to determines what properties your object now has. And this is where we get into some really important terminology. So the first thing you need to do is decide what the object looks like compared to before. So if this was your original, so this is your object, this would be called your image. So that's your image. And it has 3 things to consider. First off, which way up is it? Second, how big is it? Third off, did the lines meet or not? Now, for this one, by very quick hand measurements, I can see that that one's about yay high and that one's about yay high. So I can say that my image is bigger than my object, and we call that a magnified image. So that's the first thing. I then say, is my arrow upside down compared to when I started? That one's that way, that one's that way. Yes, it is. So I call that inverted. Now this is what your eye does. Your eye actually, its lenses inverts the image and your brain turns it the right way up again. So this is what your eye does. It inverts the image. And the third question you need to ask is, did the lines that came out of my object actually end up meeting at a point? Answer, yes they did. So because they did, we call the image real. So in a real image, we say that the lines or the rays meet. So magnified, again, if you're not sure of the terminology, it means the image got bigger. It's inverted, that means it's upside down. And it's real because the lines or the rays have met at a point. The other type of convex image you might be asked to draw, and I'm going to need to start over, is if you have one somewhere else. So I've got it here between f and 2f, so 1 and 2 focal lengths, but you may be asked to draw it where the image, or the object, sorry, is here. What if it was here? So it's now less than 1 focal length. Well, let's have a go. That goes through there, and this line, comes out here. And you're immediately seeing a problem. These two lines are never, ever, 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 ever going to meet, because that one's going that way and that one's going that way. And this is where it gets a little bit clever. So if I back my lines up a little bit, I'll see that they do meet back here. So I'm going to draw my image here. Now I know that looks a little bit like I've just done some space magic, and I understand. But because these two lines are never going to meet in the real world, I have to go the other way in order to find a point at which they will meet. And I found that point there. So now let's do the same thing as we did with this arrow and apply it to this arrow. So, compared to the object, is the image bigger or is it smaller? It's bigger. Good. So we say, again, the image has been magnified. Has it been flipped the other way up? No, it hasn't. Now I'm going to write not inverted here and then remind myself of the terminology in a moment. So we say that it is not inverted. And finally, did the lines, not the dotted lines, did the lines meet at a point? No, they didn't. Because if these lines carried on forever, they'd get further and further apart. I had to back them up to find a point at which they would meet. So we say that the image is virtual. So a virtual image is one that if you were to put a screen there, you wouldn't see it. So that's what, if you think about real and virtual, if I had, I've got one here. So if I had a screen, yes, it's a chopping board. If I had a screen and I placed it over here, I wouldn't see an image of that arrow because it's a virtual image. However, if I placed a screen here, I would see an image of that arrow over here on the screen. And I would see that because the image is real. So those are the two sort of main ones. There's one other term that I need to tell you, and this would mainly come up if your object was more than 2 focal lengths away. So I'm just going to draw it like that. I'm not going to draw the lines here. In fact, what I'm going to ask you to do as your task is to draw the ray diagram for an arrow, so an actual arrow, that is more than 2 focal lengths away. So draw your lines, maybe get a new ray diagram, so a new axis, new arrow to get away from all these messy bits, and draw it so that you have it 2 focal lengths or more away, and then tell me what the image ends up looking like. There's one more word I need to tell you, and that's the opposite of magnified. So if an image gets smaller, last word I need to tell you, we say that it is diminished. That's the scientific word for saying it got smaller. So I'm going to say you only need about 5 minutes for this task, at most. Maybe a little bit longer, depending on how you've found this explanation. But I'd like you now to draw the ray diagram for an arrow that is more than 2 focal lengths away and give me 3 bullet points to describe is it magnified or diminished, inverted or not, and real or virtual. That is your task. Good luck. All right. Hopefully you've had a go at that. You paused the video and you had a go at that challenge. So I hope that was all right, and I hope that my explanations made a measure of sense. I know normally I'd be able to come round and ask you, how are you getting on? What have you done? What have you not done? What's confusing you? And this, that, the other. But I'm trusting in your instinct that you've had a go at it. So let's go through the solution. In fact, I should just put a 2F over here. Let's go through the solution to the task that I set you. The task was, I have an arrow which is more than 2 focal lengths from the center of the lens, and I wanted you to draw the image created using the 2 rays and then describe the image using those 3 bullet points: magnified or diminished, real or virtual, and inverted or not. So let's have a look at the solution. This is normally where I get someone to come up and draw it for me, but I can't because you're all at the other side of the internet. So 1 line through the center of the lens, nice and easy. 2nd line straight across, you'll have done this with a ruler, and then through the principal focus. Bang. Just like that. So, got a point there, and then bang, bang, bang. So, in fact, I'm going to draw this with a proper arrowhead. I'm going to draw this with a proper arrowhead just to make it easier to see the difference. So, that should have been the image you ended up with. So, if that was your object, that's your image. And now we need to describe what that image is actually like. So, question 1, is it magnified or diminished? Well, through the handy-dandy measurement of eyeballing it, I can see that that one is about yay big, that one is about yay big. Therefore, yeah. So I can see that this one was smaller than that one. Therefore, the image is smaller than the object. So we say that the image is diminished, i.e. it got smaller. Second question, is it inverted or not? Did it go upside down? Well, that one's that way up, and that one's that way up. Yes, it did. So we say that the image is inverted. Now, the third challenging question is, are the lines meeting? Is the image real or is it virtual? And we see here, I follow the lines, do they meet at a point? Yes, they do. So I say that my image is real. That was all you had to do, and that is all you'll ever have to do as far as I understand it. That's not to say you can't then extend this and say, well, what if it's 3 focal lengths away? What if it's exactly 2 focal lengths away? What if it's exactly 1 focal length away? You are welcome to challenge yourself and try and do this on a more complicated level than what I've just shown you. But that was your task. So let's write up then a very brief summary of the different types of different types of image you can get depending on the position of your object. So if we say that the distance is greater than 2 focal lengths, the distance is between 1 and 2 focal lengths, and the distance is less than 1 focal length. So these are our 3 types of system. So in this case, this is what you just did for your task. We say that the image is inverted, it is diminished, and it is real. So you would go from this to something like that. The lines would meet, and you'd get something that went a little bit like that, if that was your lens. That is system 1. If you had it, I was at the start, where it was between 1 and 2 focal lengths, we saw that the image was inverted. We saw that the image was magnified. It was larger than before. And we also saw that it was also real. So we might start with an arrow like that, and we would end up with an arrow like that. Something like that, if that was your system. Bosh. Now the third one was when D was less than 1 focal length. You may not have to do this one. I didn't see it on some of the research I did, but it's worth knowing anyway. So in this case, we saw that the image was not inverted. So it was the right way up. Right way up. It was magnified. But we got a virtual image, i.e. we had an arrow up here and an arrow up here because the lines had to be tracked back from there in order to meet. So we had an image that looks a little bit like that. That is everything you need to know about how a convex lens works. And I've shown you and modelled how to do all the types of ray diagram, and you've had a go at one yourself. So that's all of convex lenses in about 20 minutes. But we can finish off the lesson with one little bit more. Let's do about concave lenses and see how they work. Alright, so the final part of today's lesson is going to focus on the other type of lens that I hinted at earlier. These are called concave lenses. Now, whereas a convex lens, you may remember, expanded around the middle and looked something a bit like that. It expanded around the middle. A concave lens does the opposite. It caves in around the middle. Now, I don't know if they designed them to do that. Probably not, because the word's a lot older. But a convex lens expands, and a concave lens caves in at the middle. So it ends up with this sort of shape. If you were to draw it in a ray diagram, which again, you're going to, then you would have something that looks a little like that. So you'd have the same symbols. Remember, your convex was 2 arrowheads outwards. That was convex. This, for a concave, you've got the lines at the arrowhead pointing inwards. And we will use that symbol again in a moment. But first, we need to see how light behaves when it passes through a concave lens. So first off, we have our principal axis. Bang, 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 bang. Just going to call that PA, save the space. And a light ray on the principal axis just goes straight through. No problems there, same as before. But when a ray of light is incident on a not principal axis point, so say here, we draw our normal, same as we did before, And the light ray, remember, bends towards the normal. Again, we're going to make the same assumption that we've got air, glass, and air. So we're going to bend towards the normal, which is going to take us sort of in this direction. And then we're here, and we have a new normal, which is over here, and we need to bend away from that. So it's going to take us in that direction. So that is how light comes out of a concave lens. I will do the same on the bottom, so it comes in here, bends a bit more. Now, where the clever bit comes in is that we can track all of these lines back a bit. Are we seeing a pattern yet? So all of these arrows, and if I drew more arrows, you'd see this, all of them appear to be coming from one point, this point right here. This is the principal focus for a concave lens. So that is the principal focus. And you'll notice, rather than being on this side, as it was before, it's now on this side of the lens. It's on the incident side, not the outgoing side. And that is a big difference, and that will really affect how the images come out when we draw our ray diagram for a concave lens. Which is exactly what we're going to do now. We're going to leave that there for a second, and we're going to write up a summary so that you have a rough idea of how they work. In fact, I don't even think I need to. I trust you to make your notes. So you'll notice principal axis is the same notes you made for concave and convex, really. Principal axis, no refraction. Principal focus, all light passes through it. However, the difference here is that all rays appear to come from F. They all appear to come from F. Remember, for convex, all rays do pass through F. So it looks like, coming out of a convex lens, or coming out of a concave lens, that all the light was focused at F and coming out and spreading out evenly. That's not what's actually happening. As you know, your rays are coming in and then being refracted, but it looks like they're all coming straight out of the principal focus. They're not. That is a key point to take away. So that is the note if you need to make it. And now we're going to do a ray diagram, or more accurately, I'm going to give you a setup and you're going to do a ray diagram of your own. In fact, I'll model one and then you could do the other. Let's make it fair to you. So, remember, that's the symbol for a concave lens. There is the principal axis over here, and here is the principal focus, give or take. So, let's say our object is here. And the same rules for convex and concave apply. So everything that you may remember about how you draw the ray diagram for a convex lens, apply it here. Give me a second to recall, go back through your notes. What do I have to do? Well, what I have to do is this. I draw one straight line off the top of the object that goes straight through the center. The second thing I need to do is draw a line straight horizontal to the lens, and then I need to draw it so that it passes through the principal focus. However, remember, light can't just reflect back on itself unless you've got a mirror. So I mock up a backwards image, and I work backwards and I carry on the ray like that to show its refraction. So you can see there, I've mocked up as I've gone backwards to the principal focus and then drawn the line outwards. And if I was anywhere else, you'd do the same thing. Now, where these two lines cross over, or where the dot and the line cross over, is where you draw your image. So here, here, and here. But I'll draw it as an arrowhead again, just because that is easier to see. So that's where you draw your image. And you should now be able to describe the three properties of that image. Is it magnified or diminished? Is it real or virtual? And is it inverted or the right way up? What it is, well, you can see, is it bigger or smaller? It's smaller, so my image is absolutely diminished. Is it the right way up or is it inverted? It's the right way up. Now, is it real or virtual is a slightly trickier question. The question you need to ask yourself is, do the thick lines meet? Do the actual light rays meet? No, they don't. The dotted line, the imaginary dotted line, and one line do meet, but the actual two lines do not. So we say that the image is virtual. So that is how you do it. Now the challenge I'm going to set for you, and your task, is to slightly change up the system, and I'd like you to draw it so that your object, you don't have to do this one because I've given you all the information that you're going to need for this lesson, but I'd like you to have a go at it if you're feeling up for it, is I'd like you to draw it so that the object is inside the principal focus. So I'm going to draw it quite small because of the way the lines are going to need to move. So have a go. Again, I think you only need about 5 minutes. Have a go at drawing the ray diagram. In fact, actually, you know what I'll do? I'll make the arrow a little bit bigger. Have a go at drawing the ray diagram on a piece of paper and then comment to me, what is the image? Real or virtual, diminished or magnified, inverted, or the right way up? You have 5 minutes and then we'll go through the answer. Okay, hopefully you paused the video, had a go. Now let's go through the solution. So first thing I do, one line through the center. Bang, excellent. Second job, line straight across and then back up through the principal focus. So dot, 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 dot. Yeah, like that. So that is how you draw it. And look at where they meet. That's where I draw my arrow. So you should immediately comment that this is just a smaller version of what you had before Tactica. And you'd be right. So I have an image that is diminished, that is the right way up, and is virtual. In fact, for all convex, I'm going to keep saying that wrong, for all concave lenses, that is always the case. So all images, I'll spell it in a minute, all images are diminished. All images are the right way up. And all images are virtual. That is true no matter the focal length. Unlike a convex lens, where it varied depending on where we were, in this case of a concave lens, you will always see that. And if you can find a ray diagram where it doesn't do that, you don't need to know it on your exam. So that's a relief, is it not? So that is everything I think I need to teach you about convex and concave lenses. That is it. That's the whole 9 yards. So if you want a piece of homework that you could do just to do a little bit of practice, I would say your task would go as follows. So your homework, if you like, if you are so inclined, I would like you to draw a table to describe the images from a lens. Images through a lens. So your table should look something a little bit like this. So you'll have convex and concave, like that. And so I'll just make that type and distance. So you've got the distance from the lens. So you're going to have less than 1 focal length. Focal length less than the distance less than 2 focal lengths. And distance greater than 2 focal lengths. You'll draw a slightly bigger table than this because I've got not a lot of space. And I'd like you, each of the boxes in the table, to describe the properties of each of the images, so real or virtual, magnified or diminished, and inverted or right way up, in these 6 boxes in the table. Hopefully that will not take you long. You can go back through the video if you need to remind yourself of any notes. And that is it. That is everything I think I need to teach you about lenses. So, if you are a GCSE physics student, I hope you found this useful. If you are the parent of one, then I certainly hope that was useful to you as well. Obviously, I haven't done any demonstrations because I'm at home right now. I don't actually own a set of lenses that I can show you this stuff, but that's the whole summary. Final question, a little challenge. Would you see the image? So what that means is if I put my screen down where the image supposedly appears, would I see it or not? Hopefully that's a quick, simple yes, no, but good checker for you. So thank you very much for watching this video. I'm not sure quite how long it's going to be when I cut it together in editing, but this has been the first science lesson that I'm going to do as part of my teaching program. I hope you found this useful, hope you found it enjoyable, and I hope you weren't too bored by having to listen to me talk so much, because it was hard to come up with activities aside from here's some teaching, do a thing, here's some teaching, do a thing. But that's what the comments are for. If you have a thing that you would like me to try and do to mix up the format, I've got some demos I can do, I might be able to do a little bit of practical work, then let me know in the comments and I'll see what I can do. If there are any topics that you would like me to cover, either in this format or in a slightly different format, also let me know. I'm going to prioritise the comments in terms of my videos, but as I'm going to be doing my own teaching practice on my own time, I will also be making videos for that if there are no suggestions for the comments. So please, your suggestions get the priority, but my students at my school also have to be considered. So thank you very much for your time. This has been Tactica Imperialis, and this has been everything that I think you need to know about lenses for GCSE triple physics. Best of luck, thank you very much for watching, and goodbye.